These are your Unit 6, Section 3 notes, and we're going to be talking about thermochemical equations. So first, remember that chemical reactions either absorb or release energy. If they absorb it, they are endothermic, and if they release it, they are exothermic. And the change in energy is an important part of chemical reactions, so chemists use delta H, or change in enthalpy, as part of the equation. A thermochemical equation is a balanced chemical equation that includes the physical states, so the little things in parentheses, solid, liquid, gas, aqueous, of all the reactants and products, and the energy change, which is usually expressed as the change in enthalpy. Now, the nature of the reaction or process described by a thermochemical equation is often written as a subscript of delta H. So, for instance, I have written down an equation down here, and as you can see, it's a carbon compound reacting with oxygen to produce carbon dioxide and water, which means that it is a combustion reaction, okay, a carbon compound and oxygen producing carbon dioxide and water, and you can see that it includes the physical states, okay, so that's a part of writing thermochemical equations. It is balanced, and then since this is a combustion reaction, and it is a thermochemical reaction, we're going to have delta H out here that's going to describe the heat released, because combustion reactions release heat, right? Which means that our change in enthalpy is going to be negative. But since this information has been given to us, it says the nature of the reaction or process. And we have decided that this is a combustion reaction. So the delta H here is actually going to include that. So it's delta H of combustion. And it is negative because this is an exothermic reaction. And this is actually 2,808 kilojoules. So this would be a complete thermochemical reaction. It includes the nature of the reaction and the enthalpy. The enthalpy is recorded with its negative side because this is exothermic. You have your states of matter. It is a balanced equation, so this would be complete. So the enthalpy or heat of combustion has the symbol like we just saw in that previous equation I just talked about. Of a substance is the enthalpy change for the complete burning of 1 mole of the substance. So that negative 2,808 kilojoules is for 1 mole of glucose. That was the burning of glucose. Now, these enthalpies, these standard enthalpies of combustion, can be found in tables, kind of like a solubility chart, polyatomic ion chart. They are known values. So I've put an example of a chart down here below. And then standard enthalpy changes have the symbol delta H, and then there's a little 0 as a superscript. And that superscript tells you that the reactions were carried out under standard conditions, 25 degrees Celsius, 1 atmosphere of pressure. Now, there are many processes other than chemical reactions that absorb or release heat, one of them being changes of state. Now, the heat required to vaporize 1 mole of a liquid is called its molar enthalpy, or heat of vaporization, with this symbol right here. And then the heat required to melt 1 mole of a solid substance is called its molar enthalpy, or heat of fusion, when it has this symbol right here. So as both of these are endothermic processes, vaporization and melting, their enthalpy values are going to be positive. But as you consider changes of state, we should realize that they kind of come in pairs. Each one is the reverse of another one. So if you think about it, vaporization or boiling is the opposite of condensation. One is going from a liquid to a gas, and the other one's going from a gas to a liquid. So they have a relationship. So those enthalpies are just going to be opposites of each other. Same value, but opposite signs. Vaporization will be positive, while condensation is going to be negative, but they'll have the same value for every substance. So same thing with fusion and solidification, melting versus freezing. So this is an important relationship to keep in mind. So if you know one of the values, you know the other one. It just has the opposite sign. So now, calculating energy released in a reaction. So notice I've rewritten the reaction that I wrote earlier in the presentation, and we're going to use this to calculate how much heat is evolved when 54.0 grams of glucose is burned according to this reaction. So the first thing that you want to remember is that these change in enthalpies of combustion, these right here, are for 1 mole of a substance. So if we know that this value is for 1 mole, and we can also say that we know that glucose weighs a lot more than 54 grams. 1 mole of it does. In fact, it weighs right about 180. So we know we should be looking at a change in enthalpy that's far less than 2808 when we do our math. So what we need to do is figure out how many actual moles this is, and then, so we're going to change grams to moles, and then using moles, we're going to do a little conversion to figure out how much heat is actually evolved. So again, our first step is to change 54 grams of glucose to moles of glucose. So I found the molar mass of the glucose and use my conversion factors. Grams are going to cancel, so I put grams in the bottom, change it to moles. I take 54 divided by 180, and I come up with 0.2, well, really, it says 0.2997. So let's go ahead and we'll round that to 0.300 moles of glucose. Now, since we know how many moles of glucose are going into this, we know how much heat is going to be produced, because if we have 0.300 moles of glucose, we know that for every 1 mole of glucose, negative 2808 kilojoules are produced. So what I'm going to do is take my 0.300 times my negative 2808, and I'm going to come up with negative 842 kilojoules. So that's how much burning 0.300 moles of glucose would produce, which makes sense. It's far less than the 2808. And so this is how you would calculate your energy released in a reaction. Of course, you'd have to know that value in advance, and we can find that in a table, or it may be given to us. So when you come back, we'll be doing some practice problems, and so be ready for that.